Hey guys, this is our lesson. It's called 5.1 Evaluation and Graphing Polynomials. It's kind of a teaser lesson to another upcoming lesson that we'll do later on in the chapter. But let's just get some basic vocab under our belts for this one. So the first piece of vocab that we have to understand is what is a degree. So you maybe remember this from before, but the degree of a polynomial is the highest exponent. The largest exponent, we should call it that. So once you've identified whether you have like an x squared, an x to the third, an x to the fifth, that's the degree of the function or the polynomial, and then we can give it a particular name. For instance, a polynomial of degree 0, meaning it would have x to the 0 power, and that's kind of a weird idea. Think about that for a minute, guys. If you have y equals x to the 0 power, well, anything to the 0 power, remember, is really a 1. So y equals 1 is an example of a constant function, these horizontal lines that are constantly giving you the same output, thus the name constant. But if you have a degree of 1, I feel like I just said something wrong there, that would be like y equals x to the first power, better known as y equals x. And these are just really basic examples of what I'm giving you for polynomials, but that's a line, so we call that a linear function. The quadratic, we just spent a whole lot of time talking about quadratic, didn't we? So y equals x to the second power would be an example of a quadratic. Again, a very basic version of it, but a quadratic. A third power, a very basic example would be y equals x to the third. The cubic function. And then you have something called a quartic function. That might be a new name for you, but anything to the fourth power is referred to as a quartic polynomial. And then a quintic would be to the fifth power. Again, there's a whole lot of other things that could be along with this polynomial function. You know, you could have coefficients, you could have other terms that are below x to the fifth. But I'm just giving you the most basic example. And then they kind of ran out of steam after that, guys. They were like, ugh, I don't think we need names for everything. So if they have something of degree 6 or 7 or 8 or 9 or 10 or so on, they just call it polynomial of degree and then whatever the degree is. So not everything needs a name in math is what they determined. So let's look at these two examples here. The first thing we want to identify is the polynomial even in standard form? So standard form, remember, is where it goes in decreasing order for exponents. So from the largest exponent down to the smallest exponent. So the name of this particular polynomial is f of x, and if I look through my terms, the first term that we should write down for standard form is actually the negative 3x to the fourth. Then it would be the quadratic term of 1/2 x squared, and I wrote too big, and then there's a minus 7 for a constant. Notice there's some missing terms there. There's no cubic term, there's no linear term. It's okay, it happens. So the next question would be, what is the degree? And remember from our last slide in vocab, the degree is the highest exponent. So the highest exponent in this problem is a 4. And if you go back to that chart, there's my arrow, a degree 4 is called a quartic. Okay, so the types I'll do in green. Pen, there we go. So quartic, like 4 quarters in a dollar, you know, that's how I remember that one. And then the lead coefficient is the number that's in front of the leading term when your polynomial is written in standard form. I didn't want to use that color, I'm going to use red. So negative 3 would be our lead coefficient in this particular problem. So this next question, it's not in standard form yet, it's still called f of x, but the first term that we would write in standard form would be 2x to the fifth. And then we have plus 6x squared. And then plus x. Again, there's a lot of terms that are missing for standard form. There's, you know, no fourth degree, there's no third degree, there's no constant, no second, no, there is a second degree, but it doesn't matter. All right, so the highest exponent that I see in this problem is a 5. And if I go back to that chart, the name for a fifth degree is quintic. Oops, I can't spell, but that's not new. And then my leading coefficient is the number that's in front of my first term when written in standard form. So in this case, it's a positive 2. So there's some vocab. So now I'm going to bring back an old concept, but give it a little bit of a fancier notation, substitution. You guys used to call this plugging in. So I could give you a function, and in this case, we have a function that's in function notation right here. And it says evaluate this function at x equals 3. So when they give you a value for x, that means they want you to plug it into the function, into the recipe, and they're going to write it in function notation. That's what this is right here. This is function notation. So it's fancy. We just have to know how to interpret it. So I'm going to take my function, which is 2, and then every time I see an x, I'm going to leave an open parenthesis, because you know me, I'm going to be using my calculator on this one. have a calculator handy. I'll have to grab my emulator, which is fine, but it is a wee bit slow. I could be in the home screen because I'm just evaluating a function, right? I already forgot what it was. All right, so I'm plugging in, I didn't finish that part. I'm plugging in a 3, right, for all my x's. And I'm just going to type exactly this into my calculator as I see it. There is something else your calculator does. It's called storing. It's kind of a neat trick. If you ever join math team, we'll show you that for sure. But for today, let's just stick to normal. I should not have done that because now I forgot it. All right, 3 to the 4th power. All right, 2. If for some reason you were trying to do this without a calculator, you'd have to really remember order of operations, and I would feel really bad for you because like right away you'd have to do 3 to the 4th power, which most kids don't remember. That's an 81. And right away you have some really significant math to do if you're doing mental math. So I hope you're never in a position where, you know, they make you do that. I know I won't make you do that mentally. All right, now instead of 5 times 3, I'm just going to write 15 because that one I do know. And then minus 7. So when I plug in or evaluate the function at 3, I get a 98. So the notation, what this would look like, is they might say f of 3 equals 98. And that means when I take my function f of x and I plug in a 3, I get 98 as my output. Remember that vocab from before. All right, so we have 2 different functions down here for 6 and 7. Again, they're both in function notation. The first function for number 6, it's 3 times, our friend the absolute value is back, of x minus 2, and they want you to evaluate this at x equals 1. So I'm going to do the same thing. And remember, you could type this on your calculator. The absolute value bar, if you remember, was under the math menu. So you could literally type 3 and then pull up the ABS feature and then 1 minus 2. That would be fine. I think I can handle this one, you know. Order of operations, there's no exponents, but absolute value bars kind of act like parentheses. So we would be evaluating this part first, right? So that's a negative 1. So right now we have 3 times the absolute value of negative 1. But we know that the absolute value of negative 1 is really positive 1. So this ends up being 3. So my answer to, I'm going to write fancy here, f of 1 is 3. That's the fancy notation. All right, same idea here. We learned our lesson earlier in this class that when we are plugging in, and we have, especially when we have a negative value that we're evaluating for, we must use parentheses on the calculator. So we learned that lesson pretty quickly in Algebra 2. That was one of the first lessons we had, actually. And it was a painful lesson for some of us. Some of us really had to get a few questions wrong before we understood it. All right, so you are more than welcome to type, more than welcome to type this in your calculator. You know, it's 7 something in the morning. I feel like a challenge right now. I'm going to try this without the calculator. Order of operations says I would do exponents first. So negative 2 squared, remember we're squaring the negative as well, so that's really a positive 4. So this problem now says 4 times positive 4, and then 2 times negative 2 would be a minus 4, and then minus 1. I should be able to do this. I'm a math teacher. All right, 16 minus 5, better known as 11. So when I took function g, this was called g this time, and I plugged in or I evaluated at negative 2, I got an answer of 11 out. All right. This is a new topic, and this is a weird one. It is a really big topic for Algebra 2. It's a defining feature of functions that we're going to start talking about kind of from here on out for all of our functions, end behavior. So end behavior is asking what happens to your function when you go really, really, really far to the left and really, really, really far to the right. And if we think about our number lines, you know, I can go to the left on the number line and keep going and going and going, and I'm approaching a number that's called negative infinity, a concept called negative infinity. And I can go really far to the right, and I'm approaching a concept called positive infinity. So whenever I see that notation, I know they're just telling me to go super far out. Now the problem is I can't actually plug in infinity, so I have to kind of think about the shape of the graph and what's going on. So the first thing I want to get straight with everybody here, this is our end behavior template, if you want to call it that. Every time I ask you for end behavior, that's what we have to write down. And sometimes if you're lucky, I already wrote it down for you, so that would be really kind. What I need you to do, though, is do some highlighting with me. The first row of end behavior here, this is one side of your end behavior. And if I kind of read this part here, it says, as x goes to, that's what that arrow means, it means approaches or goes to, negative infinity. That is a really fancy way of saying left side. Now when I look at the next row, we'll talk about this part in a minute, but it says as x approaches, or as x goes to positive infinity. So on my x-axis going to positive infinity would be the right side. So that would be the most important piece of your notes here on this slide, is that you highlight and write down this means left side and this means right side. So what end behavior is asking me is, as I look at my function, if I am a little bug traveling along the far left side, where's my bug going? Is he going up forever? Is he going down forever? Later on, we'll see sometimes they approach asymptotes. Similarly, what's happening on the right side? Are you going up forever? Or are you going down forever? So today for polynomials, there's really only two choices. Either the function is going up or it's going down on the far sides. So dyslexic teacher, this is always a good time. I really have to stop and think, where am I looking? Am I going to the left side or right side? Sometimes I'll bust out one of these just to make sure. All right, so it says, discuss the end behavior for this function. Now, if you're not sure what it looks like, you have a graphing utility. So you would just type in, into y1, you type in 4x. But I think we can all agree what this looks like. This is a line. Oops, it doesn't really look like that, but it does have a positive slope, and it goes through the origin, which isn't really important here because of end behavior, but it has a positive slope. That is important. So this part of end behavior, remember, this part right here is asking me the left side. It's saying, what's happening on the left side? So as x goes to negative infinity, if I was a little bug traveling along the left side of my function, this little bug is going down, 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 down. And the way we say down, 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 down forever is we say negative infinity. On the contrary, this part of end behavior is saying right side. So a little bug traveling along the right side of my function, my polynomial, it's going up, 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 up forever, and I'm not going to stop ever. It's going up to, we call that positive infinity. I'm just going to write infinity. So what you're filling in these blanks is just a really fancy way of saying up or down. And up is positive infinity and down is negative infinity. That's it. That's all end behavior is today. I know it seems really weird. The notation is what's really weird. And believe it or not, this notation is actually a shortcut. Actual end behavior is like a paragraph, almost looking like a paragraph proof. So when kids are like, oh, it's so long, I don't like doing this. This is the shortcut. Just remember that, okay? So this next function, again, if you're not sure what it looks like, go ahead and type that baby into y1. But this is a parabola, a quadratic function with a negative coefficient centered on the origin, but it's going to look something like this. Not exactly like that, because it's me, but something like that. So when I look at our end behavior, and I always do end behavior in the same order, I always do the left side first, just to keep it consistent. So a little bug on the left. What's the bug doing on the left? It's going down, 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 down. So we say negative infinity. All right, then we have right end behavior. What's going on the right side? Little bug traveling along the right side here, also going down, 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 down. So it's traveling to negative infinity as well. So, if at first you're like, I don't know what to write down, you can literally write the word up and down. But then at some point in your math, you have to translate that to positive or negative infinity. So keep that in mind. All right, I think, we're almost done. All right, so this function, I kind of know what it looks like, but you can pull your calculator out if you're not sure. 2x to the 4th plus 3x to the 3rd plus 1. I'm going to remember that, right? All right, 2x to the 4th. I already forgot. 3x to the 3rd plus 1. Oops, 3rd. No. Okay, x to the 3rd. Plus 1, I hope. Now, I don't need a really great graph. This is a quartic function, to use a vocab piece from earlier. It kind of looks like a weird wonky W, which is exactly what quartics typically do look like. But the idea is I need to just sketch this. Oh, no, I need to be more careful, because they also want domain and range. I'm going to need to find this minimum point here. So I'm going to use my calc feature, and I'm going to choose the minimum finder. So remember, when they ask me about left bound and right bound, they're asking for values of x surrounding that minimum value. So I can tell the minimum hits at about x equals -1. So for left bound, you can either use your left arrow to scroll over, so that way you can ensure it's definitely to the left. You could have just hopped over to like -2. That would have worked as well. All right, enter. Now, same idea, but this time you have to go slightly to the right of it. I did the wrong side, right of it. Good enough. And those two blue lines are surrounding your minimum value. So that's how we know we've done that part right. Hit enter one more time when it says guess. And we need to write down this value, which I'm going to write down on my paper. -1.12, -0.07. We'll round to the hundredth place. Okay, so we did have to use technology there. Unless you brushed up on your calculus over the weekend, I don't think anyone knew how to do that any other way. So I'm going to graph a really horrible sketch. It's actually not too bad. Let's first talk about end behavior. So I'm always going to indicate the left behavior first. If I look at my polynomial and I'm a little bug traveling along the left side here, I notice it's going up. So the way we say up for end behavior is f of x approaches infinity. And then right behavior, as x approaches positive infinity, that's saying going to the right side. So on the right side of my polynomial, also going up. All right, so now let's bring back an old but very important topic, domain and range. What's kind of neat about polynomials is polynomials have infinite domain. So no matter what type of polynomial you have, your domain will be -infinity to infinity. So that's not a big issue. But just to remind everybody, domain is from left to right. All of your x values for which this function exists, so polynomials go forever no matter what they look like. Range is going to be the problem. So remember, range is the lowest y value measured up to the highest y value. Yep. So remember, we used our technology to find that minimum piece, and that ordered pair, I wrote it down, was -1.12, comma, -0.07. So think about the definition of range, guys. It's the lowest y value. So out of this minimum ordered pair, we're going to utilize that minimum y value to start your range. So your range, and I know it's not exact, we're still going to use a bracket though, because it does go through a point, it exists. So -0.07, and then it goes up forever, so up to infinity. So, that was fun, right? There's one more question. We're going to kind of use technology, and then I'll tell you why this next question is my favorite question. So if I typed this function in, where are we at? 2x to the third, 4x squared. I'm not going to remember that. All right. 2x to the third minus 4x squared. So I can tell we have a cubic function with a positive coefficient. And if you kind of have been paying attention to what these look like, maybe you have a picture in mind. But if not, that's okay. For Algebra 2, we're going to use our calculator. Maybe that's the picture you had in mind, okay? So a cubic function with a positive coefficient would kind of squiggle like that. I'm not going to do a very good job of graphing this because I think I don't need to. In fact, you saw me put away that calculator already. I don't even need to find anything on the calculator for domain and range. We'll talk about that in a minute. All right, and behavior. Oops, I ruined my color usage. Oh well. So on the left side of my function, I'll do this one in black. Didn't even look like that. Okay, left side. Little bug traveling along the left side. It is going down, 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 and we call that approaching -infinity for f of x. The y's are going down is what's happening. On the right side, we're traveling up, 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 which we indicate as a positive infinity for f of x. So there's in behavior. Now this is why I was very happy to see this question on a domain and range question, because an odd degree polynomial, so like a linear or a cubic or a quintic or a 7th degree, the ends are going to go in every direction. So it's going to go forever to the left and right. We already knew that about domain. But the range is going to go down forever and up forever. So I don't have to utilize any sort of technology for a domain and range question when it's an odd degree polynomial. That's awesome news. So we know the domain is negative infinity to infinity, and the range will also be infinite, from negative infinity to infinity. So that is our intro to this concept of investigating graphs. We're going to dive much deeper into this later on in the chapter, but we got a lot of vocab today. We got the degree, the type of function, we talked about standard form a little bit, we hit our first intro for end behavior, and then we brought back old concepts like domain and range. Good luck, everybody.